Hello friends, welcome to Joy of Life. Today we are going to do the second problem. The problem number is 116. It's a medium level problem that says populating next right pointers in each node. So the problem says you are given a perfect binary tree where all leaves are on the same level and every parent has two children. So this is the definition of your perfect binary tree. So you have all the leaves are on the same level and every parent has two children. The binary tree has the following definitions. So it has this next val, it has a left subtree, the right subtree, and a pointer to the next. So we need to populate each next pointer to point to its next right node. If there is no next right node, the next pointer should be set to null. And initially all the pointers are set to null. So initially all the next pointers are set to null. Okay. The follow-up part without any extra space, we are going to see that in a different video. Before that, let's look at the problem in details. So here we have been given a tree wherein we have the root 1 and then 2, 3, left and right child, then 4, 5, the left and right child of 2, and then the 6 and 7 as the left and right child of the node 3. So they want each of this node to have a next pointer, so this extra pointer, and it should point to the next right node. So in case of 1, there is no next right node, so it points to null. For 2, there is a next right node which is 3, so it points to 3. So for 4 it points to 5, for 5 it points to 6, and for 6 it points to 7, and there is nothing on the right of 7, so it points to null again. So let's see this problem in much more details on the board. So we have this node 1. So it has two nodes, the left tree and the right tree. The left one is pointing to 2 and the right one points to 3. So 2 has again two childs, so they are 4 and 5, and 3 has two child, one is 6, the one is 7. And each of this currently is pointing to the next pointer. So ideally a tree like this will have a left and the right pointer, right? But in this case we have been given an additional pointer which is called the next pointer. So for all the next pointers it's currently pointing to null. And what we need to do, I'll just depict with different color, as you have already seen that this guy need to point to 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 this. So there are various way in which we can traverse a tree. The way that we are going to look at is called the level order traversal. So wherein we'll be going by level by level. So let me write down the name, level order traversal. So what happens on level order traversal is we go level by level. So first we'll look at this level, then at this level, and then this level. So first we'll look at the level order traversal algorithm, and then we'll see how we can use that to solve our problem. So what we are going to use is we are going to have a queue. So initially the queue is empty, and as you might have noticed in this in this problem is that we have been given with a connect function that takes the root node, and we need to return the node after we have made modification to the tree. So we have been passed with 1. So what I'm going to do is I'm going to put 1, and then I am going into the queue. So just to give you a quick recap, so queue is a FIFO data structure. So it means first in, first out. It means first in, first out. So whatever goes into the queue first goes out first. It's like a normal queue. for a movie ticket or anything. So you have a queue like this. So whoever enters the queue, so this is your entry, this is your exit. So this is entry and this is exit. Okay. So we put the root element and we start the uh, loop. So we start to iterate and we iterate until queue is empty. At every point what we are so we will denote the queue with the character queue. Okay, so we get the size of the queue. So at every level when we come to the top of this loop, at every level whenever we do a queue dot size, we'll get the number of elements which represents the number of elements present at each level. So you can see that at the first level you'll have one element, then two, then you have four elements, and then if we have childs here, so let's see if we have child, how many elements we'll have. So we'll see that we'll have 8 elements. So 8, 16, and so on, right? So it will grow like this. So at level 1, there will be only one element, and if we do a queue dot size, we'll see that we'll get 1. And what we are going to do is we are going to have an inner loop which will start from 0 to size. So this loop will now since I got a size of 1, so this loop is going to iterate only one times. And what I am going to do inside is we are going to do a queue dot poll. So what does poll do? Poll removes the element from the top of the queue. So what we have at the top of the queue, that is 1. So we get 1 here, the node 1, not the integer 1. So here also while keeping, we have kept the node 1, not the integer 1. So now what we are going to do is we are going to add to the queue. Definitely we'll check for null. Add to the queue that we got the element in E. Then we are going to put E dot right and um, E dot left into the queue. So when I say E dot left, I mean the left child, which is 2, which will be added here. Again, this is not the integer, but the node itself. And E dot left, which is 3. So they are added to the queue. And this loop, which is meant to run only one time because the size was 1, will now exit and it will go and check if the queue is empty. So the queue is not empty at this point. So what do we get in the size now? We get 2 as the size now. You can see at each level how we are getting these numbers automatically since it's a perfect tree. So what we are going to do, we are going to do a e dot poll again. So we're going to remove 2 and what we get here is a 2 now, right? And what we do, we add its 2's left and right child, which are 4 and 5. And this loop will iterate because the size was 2, right? So it will iterate once more, and it will remove. So what it will get out of this poll method is 3. I've chosen a different color. Sorry. So what we'll get is a 3. So we'll add 3, add to the queue 3's left and the right child, which are 6 and 7. So 6 and 7 is also added to the queue. So this loop was supposed to run 2 times. Now it will go up and we'll check if the queue is empty. The queue is not empty. So what size we get? 4. So you can see that how we are going smoothly going level by level. So now what happens is there is no left and right child for 4 because it's a leaf node. So it will be removed, then 5 will be removed, 6 will be removed, and 7 will be removed. And the queue becomes empty and we go out of the loop. So you can see here that on my first pass there was only 1. On the second pass there was 2, 3. On the third pass there was 4, 5, 6, 7. How we have gone level by level on our iterations as well. So we are going to leverage this in order to connect the nodes. It will be very similar to what you have seen so far. So what we are going to do now is very similar. So let me first put down whatever we have, and we'll do a little modification. So we will say iterate uh, until queue is empty. The condition remains the same, and we are also going to get the size from queue.size. But yeah, then we'll have some modification. So when we just keep in mind, so we are getting elements like 1 2 3, then 4 5 6 7. So if you look at this diagram, the last element does not need to be processed. So 1 was the last element in the first pass, right? Yes, since we have only one element. So it was both first as well as last. In the second pass, we have 2 and 3. For 2, we need to do something, but for the last element, we don't need to do something. They should point to null, and as the problem says, it is already pointing to null. And for 4, 5, 6, 7, we need to update 4, 5, and 6 and not do anything with null, with 7. It's already pointing to null. So you can see that only 4, 5, 6 is required to be processed. So what we are going to do is a little modification from this loop. So what we're going to do is we are going to do from I0 to size minus 1. Okay. So the last element we are not going to process at all because we don't need to process it. It's already been set to null. And now we are going to do something very similar that we already did is we are going to do a poll. So once we do a poll, we get this element E, and what we are going to do is we have to populate its next pointer, right? So what we are going to do, the next element that we have is we can get that element using the peek method. So poll method, it removes the element from the queue, but the peek methods returns you the element but does not remove from the queue. So now if I go by this algorithm that we are writing here, so what happens is for the first level, when let's say this is my queue, let me draw the queue again. This is my new queue. So when I put 1, this loop will not at all come into effect because size minus 1 is 0, 0 to 0, it will not be processed. So outside this for loop, before it goes and hits the iterate method, what I need to do is I need to do a e equals to q dot poll again. This is for only the last element that we are doing, and we are going to add e dot left, and we are going to add e dot right. So this is only for the last element. What we are doing is once we are removing one and putting its both the childs here. So next time, so these are added, and it goes over here. So we get 2. So this loop will run only one time. So it will run only for 2. So we do a e dot q dot poll, and we get 2, right? And what we are doing in 2's right, that is over here in 2's right, this statement in 2's right, we are putting q dot peak, which is 3. So you can see that we are putting 3 to 2's next pointer. And what we'll do over here is we'll add to the queue e dot left and q dot add e dot right. So you can understand clearly from here that only for all but the last element we are populating the right pointers, and for the last element we need to add the child and remove it from the queue. That we are doing it outside, and here that's why we are iterating. Let me put a boundary here. So here we are just iterating from 0 to size minus 1. And for the last element, the one we have skipped one element by doing a -1. For last element, we are not populating the right pointer. We are just taking removing it from the queue and adding its child so that we get the right number of elements on the next pass. So this is the whole intention behind splitting up this entire size into size -1 over here and just one element over here. So we'll check how it looks in the code. So what we are going to do is if first we'll just have some regulations check. If root equals to null, then we don't need to do anything. We can just return the root. Okay. Otherwise, we'll need a queue, and the queue need to store the node. So the name of this uh, structure is node, and let's call it queue. So and we are going to create a linked list. Okay, and then what we are going to do, we are going to add the root to it, and we are going to iterate until this queue is empty. So until it is empty, we are going to iterate it. So as I told you, the first thing that we'll be doing is to get the size. So we'll do a q dot size, and we are going to iterate till size -1. So for the last element, we'll just going to grab the elements and we are going to put it. Nothing else we are going to do. So what we are going to do over here is to get the element in E, and we are going to say q dot poll, and on E dot uh, next it is right. Next we are going to put q dot peak. So it's just going to get peak the next element, and we are going to put that element over here, and we are not going to do anything, right? And we are going to add. So we are going to check that if these nodes that we got e dot left not equals to null, then q dot add e dot left. So we're going to do a null check on the left and the right child, and we are going to add them to the queue. It could happen that it's a leaf node, it might not have a right child. So this is just a regulation check. And outside this for loop also, so we have done this for the size -1 elements. For the last element, we are going to do the same thing that we have done earlier. So the same thing we are doing over here. There is no change. And what happens when we exit this loop? We are going to return our same root because we haven't created a new tree. We have modified the existing tree. The tree that was given to us, we have made modification on top of that itself. Let's run this and see how it goes. So you can see that it has been accepted. So let's do a submit and see how you're getting the result. So yeah, it's submitted. It was done in 2 milliseconds, faster than 45% of the submission. As always, I'll leave the optimization up to you. My intention is to give you the approach on how to solve it. I hope you got the intention or the idea behind how we are going to approach and solve this problem. So yeah, this is all from this video. Do share, like, and subscribe. Let your friends know. I need a lot more motivation. We are nearing almost 100 subscribers. Um, Hope to reach 100 soon and then 1000. Um, Please do like, share, and support me in creating more videos. Thank you and have a nice day. Bye bye.